Yeah, thank you, Antonio, and thanks very much for inviting us. So, we have heard now a lot about different processes, and with my talk, I want now to focus a little bit on yield quality and speed and how important it is to have a laser pulse control in semiconductor applications to boost these parameters. Yeah. Okay. Now it's moving. Okay. So what I'm talking about today, first I will dive a little bit into challenges for laser manufacturing in the semiconductor industry. Then I want to make a little exercise and have a look at the relation of laser stability and production yield that we have. I want to give you a little bit of an overview. What is our focus in this very big field of laser manufacturers? I want to show you what is this Pulsecore laser control that we have developed. And finally, I want to give you two examples. One example where the energy stability is very important, and the other one where the timing stability is very important. So let's get started with the challenges for the manufacturing in the semiconductor industries. And we have seen a lot of examples already this afternoon. For example, if you take a 4K UHD display, it has almost 25 million LED chips on this single display. And you need a crazy high yield. If you have a crazy high yield, for example, from 99.999%, you still have almost 250 defective LED chips on a monitor. And this really puts a lot of stress on the production equipment and on the manufacturing, because you can see if your yield in the manufacturing just drops a little bit, you're producing a lot of crap and you don't have a lot of good components. Let's stay in the LED manufacturing. A second challenge for the manufacturers is, in the past, we were talking conventional LEDs that are size of 100 micron to 1 millimeter. Now we are talking micro LEDs that range from in the range of 1 micrometer up to 30 micrometer. So we need much more precision here at the same. And in the next, we already got the example for the through glass vias. An 8-inch wafer has 9 million through glass vias to be installed. This means you need a crazy fast processing time. Otherwise, the process will never get cost effective. Yeah, you see, even if I do 1,000 holes per second, it will take 150 minutes to drill these 9 million TGVs into the hole. So you need to be very fast at the same time. And the third or the last one is, of course, for example, in silicon processing, you always need to develop new wavelengths, new technologies, new ideas to make the next breakthrough technology. And what does this now mean for the laser manufacturer? We already had the example with the LED screen with the 25 million pixels. You need really excellent process stability. This is really the key for the yield in the production. You need this very high submicron precision, and this asks for advanced and process skills from a manufacturer. You need this crazy high process speed because it's so many components on one device. So here productivity really matters. And the last one, innovation for new processes, for new technologies, like using mid-infrared femtosecond lasers, like we've already seen before. To get you a little bit more aware why I'm always talking about so much about yield. We're talking about now, like any laser process you have a statistic distribution of your laser parameter, be it energy, be it pulse-to-pulse stability, be it the timing between the two pulses. You always get a statistic distribution of your laser parameter. And in the process, you always have a field an acceptance range where your part is considered a good part. If I apply the laser and it is inside the green box, you can say it is a good part. If I'm on the outside, I'm creating faulty parts. So the idea is now to get as much as possible, to enlarge the green box as much as possible to create less and less faulty parts. And now it is very hot and it is now a complicated diagram, but we can manage together. What I show here is on the y-axis, I show you the average number of defects on a device that has, for example, 1 million components. Yeah. And on the x-axis below, I show you the green box. If the green box is 2% from the, or 3%, 4, 5, or 6% from the average laser parameter. And what we are looking now, and the bars that I've printed here for you show you how many defects will a laser with a stability of 1%, 2%, 3%, or 4% produce if the green box has the size like it is shown here below. And the important takeaway, and this is a bit surprising, because if we now compare a laser with a stability of 1% to a laser of a stability 2%, one might say, okay, it could produce probably 2 times the defective parts. But look at this area. If we look here, the laser with the 1%, you get less than 1 defective device per component. And the laser with the 2%, you end up with more than 10,000 defective parts. And this is very important to have in the back of your mind, that the stability of the laser really, really matters once it goes to yield. Yeah. And while this laser might be acceptable, this laser probably is not. And this brings me to the next slide, and this is where to focus in the semiconductor industry. And for a laser manufacturer, there's 2 different ways where you can focus. You can enter the race for the maximum power. And this is not what we do, but the Luxinar way is we go the way we want to maximize control and stability. Because of the chart I've just shown to you, we believe, and our experience is, this will bring much more benefit to the industry than bringing a laser that has, again, 20% more output power. So what does Luxinar provide for this? And we call this Pulsecore technology, and I could talk for an hour and a half if we had the time, but I will want to make it very short. Pulsecore is a combination of features that we have put to the laser, and I want to bring it down to 3 simple points. Pulsecore is the most precise, fastest way with the highest stability in both amplitude and timing to control laser pulses. This is what we are standing for, and this is what our focus and development is for. What does this mean for you? It means fast pulse energy switching. You can switch pulse energy from pulse to pulse. Of course, if you can control any pulse, you can also control the first pulse perfectly good. It gives you a smart pulse control. We name this because you have the complete freedom of a pulse on demand combined with amplitude modulation that you can do from pulse to pulse. So you have complete freedom as well as in the energy range as well as in the temporal range. And a very important point, and this is where we put a lot of effort into, pulse to pulse stability is greatly increased by this technology. We typically have a 50% better pulse to pulse stability compared to our competitor. And in the slide before, you've seen this can bring up, for example, production yields up by a factor of 10,000. And this can really be a big thing. Now, 2 very quick examples. This is one example that is something that is there for years. Yeah? I'm talking here about soft wafer marking on silicon. A lot of people have tried it. It is you're melting some dots inside or on top of the silicon area. It is a very a process with a very small process window. You need to control the depths of this dents you're making to the surface to a sub-micron precision. And the whole process needs to be completely debris-free. And with these Pulsecore technology, we have really unprecedented repeatability for this process. So this is something where the pulse-to-pulse stability of this laser, which is far below 1%, really is the big differentiator and just makes this process possible. And the second one is, again, the example with the TGVs that we've seen before. It has super high speed requirements. We are drilling one hole in 200 nanoseconds. And the thing is, we need 9 million holes. So we need to drill on the fly because we cannot stop the beam or the target, because the time required to stop the galvo and move the galvo again will ruin the whole process. Yeah. So, and if, for example, we take a beam speed of 10 meters per second, which is what scanners can achieve, this, on the other hand, will now require pulse on demand, because they are not the vias you want to do. They are not in a fixed pattern, but they are in a random pattern. So you need to be able to control the firing of the laser with a high precision. And if I take the target precision, lateral accuracy, what is required in the more advanced ones, which is 2 micron in a 6 sigma, you're ending up with a maximum trigger to light jitter of 33 nanoseconds. So you need to have a pulse on demand mode that can deliver you the laser with 33 nanosecond. And on the right-hand side, you see here now how the result looks like. In order to being really fast, we are drilling very small holes with a super small taper. You see it is a 550 micron glass. We are drilling a 2 micron holes through it, and the taper is less than 800 nanometer on a 550 micron hole. So the hole is really very, very straight. The reason why we do it, if we make the hole bigger, you end up with this egg timer shape, which is absolutely not accepted in the industry. The process is usually followed by some etching. And with it, so you're just making the initial holes, and then you could put it to parallelize the process again, put it in the bath, put it to the etching, and etch it to the diameter that you want to have it. Yeah, that's my 2 examples. And I come to my conclusion. What we can offer is this Pulsecore technology, which is essential to optimize the production yield in these semiconductor applications. Our Pulsecore technology offers the highest level of pulse laser control. And what I ask you is contact us for 2 reasons. The first thing is, if you have applications that can benefit from using this Pulsecore technology, you are very welcome to contact us, but also the other way around. If you have technologies that can contribute to this laser control or stability that we are doing, we will also be very interested to make a connection and discuss about ways how maybe to even further improve the laser technology that we have in-house. And with this, I'm on my last slide. Thank you very much for attending. Antonio, thank you very much for inviting me here. And
thank you very much, Martin. Thank you for the presentation and for giving us this point of view of how to control also the characteristics of the laser. So we have time for the questions for this final speaker. I have perhaps a question regarding the combination of your technology with the beam shaping technology that we discussed at the beginning. So I don't know if you explore how your pulse control technology combine it with beam shaping. That is a topic that we hear a lot in different applications to improve the efficiency on the process, can also go in the direction of having more and more control of the process. I don't know if it's something that you explore at Luxinar, or for the moment you focus in the development or on your technology.
Yeah, we are not developing these beam shaping technologies, but of course it is also a very good and essential combination. For example, you use a laser flat top because your process window is so small and you cannot not work with a Gaussian beam because you will probably damage underlying layers. And so you're moving to a flat top, and you move into the flat top for the reason that you need to have more energy control. And I'm combining the flat top with the possibility to even better control the pulse energy. This will be a double benefit on the process. So I'm yes, our lasers are very successfully used in combination with the beam shaping also.
And do you think this Pulsecore technology will be used in the different lasers you have in your portfolio, or perhaps will be for some selected products that are more directed to these applications you mentioned?
No, we don't have this in the CO2 lasers. Yeah,
Hmm.
but we have this in the nanosecond and femtosecond lasers that we are
Okay,
producing.
so both nanosecond and femtosecond.
Yeah. Yes.
Okay, very good.